Hello, welcome to another video from the conscientious biologist, Ben Gallagher. This one's the fifth one in the body communication series, and I'm hoping you've come here having just watched Body Communication 4, which looked purely at the structure of the human eye. We will do a very brief recap of that at the start of this video, but this one looks more at two major parts of how the eye controls vision and what you can see. The first one of those is the role of the iris to control how much light comes in and out of your eyes, and the second one is looking at how the eye is set up to focus on distant and then close objects. So that's what we're going to be running through in this one. It's all from the GCSE syllabus, and as always, please do subscribe to my channel if you haven't done so already. Thank you. So let's do that very quick run through of the human eye as the receptor organ for light. This is purely so that we can put everything else in this video into context. So remember, the eye is basically spherical, and that tough outer layer is called the sclera. That's the white layer around the outside. Inside of that, you've got a liquid called the vitreous humor. So that makes the eye this kind of bag of fluid. Now, the front of the eye, if you remember, kind of bulges out and is transparent. That's the cornea. The cornea is transparent to allow light to come through into the eye. The internal lining of the eye is this black layer, this choroid, and that's to prevent internal reflection, to prevent the light bouncing all around in there. You've got the iris. This is the main thing we're looking at in this video. The iris is an extension of the choroid. It's the coloured part at the front of the eye. And if you remember back in the last video, it was at this stage that I flipped the diagram to front ways on so you could see how those different layers match up to each other in the more front-on view that we're familiar with. That's the iris then. So at the back of the eye, you've got the retina. This is the photoreceptive or light sensitive layer that picks up the signals of the light, deals with them and sends that information down the optic nerve to the brain. Within the vitreous humor then, kind of behind the pupil, which is the hole through the iris, you've got the lens. That's what we're going to look at as the second thing in this video. And you've got ciliary muscles and suspensory ligaments that hold the lens in place. In front of that, you've got a fluid called the aqueous humor that just fills out the front of the cornea to make sure it keeps its shape. So those are all the main parts of the eye and quickly their functions. But the last video looked at that in more detail. But you must know all of these if you're going to understand what we're going to go on to next about how the eye actually sees and manipulates some of these parts. So let's look at the role of the iris then. Now, the iris controls how much light enters the eye. It's a relatively straightforward process, but here's the front on diagram I just referred to. So you can see the pupil, the black center, you can see the iris around it. In this case, I've used a blue eye, but that's the iris. Then you've got the sclera around the outside of that. So the reason you can see the iris is because you're looking through the transparent cornea at the front of the eye. Okay, but remember, the iris is kind of an extension of the choroid that comes in, leaving that gap in the middle, that hole that's the pupil. That's how light's going to get in. Now, within the iris, you have a couple of different layers of muscle. The first one of those are these. These are circular muscles. Easy to remember because look at them, they're circular. There's several bands and several lines of them going round. And if you look very close up at your eye in a mirror, you can kind of see it's slightly more zigzaggy than I've shown on my diagram, but you can see the kind of circular muscles going around in your eyes. Now, if you enter a situation where it's bright light, okay, lots of light, you don't want too much of that light going through your pupil because it could damage the retina at the back. So you need to limit how much light goes into your eye. So somehow you need to shrink your pupil down. Well, that's where these circular muscles come into their own, because those circular muscles, if you watch the diagram as I just did there, the circular muscles constrict, and because they're circular, when they tighten, they shrink in that way. That pulls the iris round over the pupil and shrinks the pupil down. So you can see on that far diagram, it's gone much smaller. This is why in bright light, if you look at someone's eyes, their pupil appears really small. That's because the iris has pulled in as much as it can to limit the light that's getting to the retina. Now, the opposite is true in that the pupil needs to get bigger in dim light, and that's because of these muscles, a second group of muscles within the iris called radial muscles. Now look at those are lines that literally radiate out from the center. So I put those in slightly bolder yellow to differentiate them, but you can see they radiate out. Just think when you were a kid and you drew a picture of the sun and you draw lines coming out from it, because that was the light radiating from the sun. That's why they're called radial muscles. Now what the radial muscles do is they go through the iris in that direction. So when you go into dim light, those radial muscles can all pull in, and look at how that will affect it on here. If they pull in, they will pull the pupil open. They'll shrink the iris. So you've got all three, kind of normal in the middle, you've got dim light above me, you've got bright light over there. But let's just kind of try and summarize that in a table, because this is what you'd need to put down in the exam. The conditions, bright light and dim light, which muscles are involved. You must mention these in an exam, in your answer in the exam. In bright light, the circular muscles contract, they pull in, but the radial muscles must relax so they can just stretch out and open up. The opposite for dim light, in that the circular muscles relax so they can go nice and loose and open, because the radial muscles are going to pull in to pull that pupil open as much as it can. The pupil, therefore, will be small in bright light and large in dim light. And the reason for that is that in bright light, it restricts the amount of light entering the eye, so protecting the retina. And in dim light, it increases the amount of light available, which will enhance vision. Now, you absolutely will have noticed that. Anytime you've been in a room that was quite dim and you step outside into the sunshine, you probably go, ah, that's too bright, it hurts my eyes. That's because your eyes are reacting, they're hurting, and those radial muscles, the circular muscles have got to pull in to quickly close up that pupil. But then after a minute in the bright light, you go, oh, doesn't feel so bad now. It's because you've limited the light, you've pulled your iris as thick as it can go to cover up the pupil. It's the same if you're in bed at night, you're reading or whatever, you turn the light off and it's like, wow, the room looks really pitch dark. But within a minute or so, you start to get used to the dark and you start to see things. That's because your pupil has been pulled open by the radial muscles, massively improving your night vision, which of course has an evolutionary advantage, is huge, because it means you can see predators at night time, you can find safety, you can find shelter or whatever else. So take a screenshot of this one. This one comes up in the exams almost every year. This is the role of the iris. Take a screenshot and then we'll move on to focusing. You'll notice I put the title up there as focusing and accommodation. It's because the word accommodation kind of means the same as focusing. Focusing is how your eye can change to allow you to clearly see objects that are far away or objects that are close to you. In other words, you're accommodating that distance, you're being very accommodating to it by allowing your eye to adapt and change to give you a clear focused image on your retina. So accommodation kind of means the same. So let's pull up our picture of the eye again in cross section, and we've got the main things going on here. We've got the suspensory ligaments, the ciliary muscle, the lens and the retina. These are the four key elements involved in focusing and accommodation, because to see anything clearly, the image must be precisely projected onto the retina, as in the image must converge and focus on those retinal cells at the back. Can't be in front, can't be behind, must hit them exactly so you get a clear, sharp image. Now to do this, you need to bend the light as it comes into the eye, but the correct word for that is refract. You've probably done refraction and reflection in your physics lessons, so this should be familiar. All we're talking about is when light enters an object of a different density or a different medium, the light can change the angle that it's traveling at. So you need to change that angle to focus it onto the retina. Now, if we've got an object that is a long way away, a distant object, then the light from that object is going to be traveling towards the eye roughly parallel the light rays. Because it's a long way away, the object's going to appear small, it's going to be traveling roughly parallel to the lens. Now that means the lens, as you can see here, can be relatively long and thin, because we don't need to bend that light very much to get it to all converge and focus and hit the retina at one point. So a thin lens won't bend the light much. If you look at the angle between the light coming into the lens and the light it's now bending it at, that angle is very, very small, okay? Or the angle that it bends it at, sorry. Doesn't need to bend it very much. Whereas, if we flipped it around and we looked at something at a different distance, then we need to be able to change our lens to accommodate that. So now if I change it to something that's very close to the eye, so you can see the light rays now, because it was a close object, the light rays can be expansive to come to the eye. Look at the lens. It's got to bend those light rays quite a lot now, because they were coming at that angle. It's got to bend them a long way back to get them in. So the lens as it is won't do that job. So this is where the ciliary muscles and the suspensory ligaments play a role. The ciliary muscles need to change their shape, and what they do is they pull inwards that way, so they contract, and if they pull inwards that way, it makes them longer in that direction. It pulls in that direction, it pops up. If you tense your bicep muscle, if you shrink it that way, it pops up that way, if you see on big muscly people. So by pulling in that way, it can lengthen. That allows the suspensory ligaments to slacken a bit, which allows the lens to stop being pulled so long and thin, and it can relax back to a thicker shape. So if we put the lens back in now, with those ciliary muscles contracted that way, so they lengthen that way, the suspensory ligaments can relax a bit, the lens can go and relax back to a fatter shape. Now that it's much fatter and thicker, that will bend the light to a much greater degree and focus it onto the retina. In other words, all we need to do accommodation of light is change the shape or thickness of the lens so it can bend the light to a different degree. Now, I should also mention at this point, your cornea also plays a massive role in bending the light. But you'll notice the cornea doesn't change shape. So the cornea always bends light to the same degree. It's the lens that then has to do a secondary refraction of the light to get the fine focusing. But we're not going to worry about anything about the cornea. I haven't even changed the angles of my arrows as they go through it. Don't worry about the cornea, other than to know it's the cornea and the lens that refract the light, but it's only the lens that can be adaptable, so do the fine focusing. And this is called visual accommodation. So that fine focusing, that contraction lens, that's visual accommodation. Now, let's try and summarize everything we've just put in one screenshot so that it's all there and obvious for you. On distant objects, the light's coming in relatively parallel, so the lens can be thin, so it doesn't need to bend the light very much to focus it on the retina. So these 4 points are what you need to mention in the exam. The ciliary muscles are relaxed. That means they're more spherical. The suspensory ligaments are therefore tight, so they pull the lens flat, so you don't get much refraction. When it's a close object, those ciliary muscles that were nice and relaxed and spherical are going to pull inwards like that, tense in that direction, so become longer. Because they're contracted and become longer in that direction, shorter in that direction, that's the contraction, which means longer in that direction, the suspensory ligaments loosen, the lens will relax and thicken, so you get a high level of refraction. That's kind of a summary of what we've just talked about for focusing and accommodation. But one last thing I want to put on this slide before you take a screenshot of it, and that's when there's issues with focusing and accommodation. So eye defects, but specific to defects with accommodation. Now what we're talking about here is being short-sighted and long-sighted. You may be short-sighted or long-sighted, and you may need glasses to give you an additional layer of refraction to bend the light correctly for you. But the correct terms for these, if you're short-sighted, it's myopia. And if you've got myopia, that means you can't focus on distant objects because you're short-sighted. You're good at sighting the things that are short distance from you. You can't focus on distant objects. Now, why you can't do that is because if you've got a distant object, so look at the top one over there, to see distant objects, you need to get your lens really flat. Now, if there's a problem with your eyes that you can't do that, you can't get the lens flat enough, you're not going to focus the light correctly, or maybe your eyeball is just a bit too long, literally the shape of your eyeball is too long. So you are focusing on what should be the correct spot, but the retina is a bit further away in your eyeball. To put it more clearly, look at this diagram up here. On this diagram up here, we've got distant light. So we've got the light coming in from quite a distant object, relatively parallel, but the lens isn't thin enough isn't thin enough and it's refracting the light too much because it's thick, which means the focus point, if you look where I put the X, the focus point is well in front of the retina. That could be because the lens is too thick or the eyeball's too long. Either way, it's trying to focus in front of the retina, which means you're not going to get a clear image on distant objects. With the opposite of hyperopia, which is long-sightedness, you can't focus on close-up objects like the bottom one over there. And think, for focusing on close-up objects, you need your lens to be really thick. So either the lens can't go thick enough, maybe you can't correctly contract your ciliary muscles, or maybe your eyeballs are a bit too short and a bit too small. Either way, in that case, this diagram is now going to be true, that the focus point, if you look where the light rays now converge, it would be beyond the retina. Now, obviously, the light isn't going to burst through the back of your eye and be focused on the back of the retina, but it means it hasn't had chance to focus before hitting the retina. Either way, with these two, your image is going to be blurred. So that's how short and long-sightedness work. Those quite often come up in the exam as well. So take a screenshot of this one and this one, plus remember the slide that we did on the role of the iris, summarize everything that's in this video. So your next lesson will still be staying on body communication because this is still key processes for how your body's sensing around. But we're moving a little bit away from specifics of the nervous system, specifics of the brain, specific of receptors like the eyes. And we're looking at an overall process called homeostasis and one specific example of that called thermoregulation. Homeostasis is how your body keeps everything at a constant within you. So head over to that one next, please. As always, please do subscribe to my YouTube channel if you haven't done so already. Give this video a like if you find it useful, and remember there's loads of useful information for your exams on my Facebook page as well. Thank you.